This problem is about the fundamental relationship between surface charge and electric fields. So here we have a spherical conductor. Let's say it has radius A, and we've put some charge Q on it. So the charge will reside on the outer surface of the sphere, and the electric flux will emanate out in the radial direction. So from the symmetry, we know the form of the electric flux density field will be a component only in the R direction and only depending on R. So let's select a Gaussian surface that will have the same symmetry as the electric flux density field. So our Gaussian surface will be a sphere of radius r, where r will be greater than a, the radius of our spherical conductor. So now we're going to apply Gauss's law that the charge enclosed is the integral over our closed Gaussian surface of d dot ds. So here is our surface differential, so it will also have a direction in the radial direction. So we'll have an AR dot AR, which is 1. This is the electric flux density on the surface of this sphere of radius r, and it is constant everywhere on that spherical surface. So this integral becomes the value of the electric flux density field on the surface of our Gaussian surface, and the integral of ds over the whole surface of that Gaussian surface of radius r. So that's just the surface area, 4 pi r squared. So our electric flux density field is Q over 4 pi r squared in the a sub r direction. So let's calculate the electric flux density field right at the surface of the sphere. So the value will be Q over 4 pi a squared, and 4 pi a squared is just the surface area of the sphere. Now let's calculate the charge density on the surface of our sphere. Okay, so the charge density will be the charge on the sphere divided by the surface area of the sphere. So the magnitude of the electric flux density field on the surface of the sphere is the same as the charge density on the surface of the sphere. And that makes sense because for every 1 coulomb of charge emanating from it will be 1 coulomb of electric flux. If we draw a unit vector pointing out from the surface, notice that when the electric flux density field is in the same direction as this outward normal, the surface charge is positive. If the electric flux density field were in the opposite direction to the outward normal, it would mean that the surface charge is negative. So here is our conductor phi equals 0. So here is the electric field intensity for the region above it, and here's the electric field intensity for the region just below it. So there's a negative charge on each surface, and because of the larger magnitude of the electric field above, there's more charges on the top of the plate than on the bottom of the plate. Now to find these charge densities on the surface, we need to find the electric flux density field on the surface. So we can obtain that from the electric field intensities by just multiplying by the permittivity of free space epsilon sub 0. So after doing that, we get the electric flux density field on the top surface of the plate and on the bottom surface of the plate. On the top side of the plate, A sub phi is in the same direction as an outward normal. So on the top side, the charge density, the surface charge density, will just be equal to our value of our electric flux density field. Now on the bottom side, the outward normal is in the opposite direction of A sub phi, so our surface charge density on the bottom side will be negative the value of our electric flux density field on the bottom.